I will estimate the value of lambda max of 1,3-butadiene. We learned that the energy of the particle in the box is quantized, and its total energy is equal to n squared times h squared over 8ma squared, where n is a positive integer. So we'll use this equation to compute the lambda max of 1,3-butadiene. In 1,3-butadiene, there are 4 pi electrons being delocalized within this carbon chain. CH2, double bond CH, single bond CH, double bond CH2. This carbon chain is approximately a one-dimensional box despite its zigzag shape. If we look at the 4 pi orbitals of 1,3-butadiene, we find that in the lowest energy pi orbital, there are 0 nodes. In pi 2, the second lowest energy orbital, there is 1 node here in the center. In the third lowest energy orbital, we have 2 nodes, and then in pi 4, we have 3 nodes. The more nodes, the higher energy. And since we have 4 pi electrons, they occupy the first 2 lowest energy MOs. And therefore, we may approximate this 1,3-butadiene as a particle in the box problem, and we say this pi 1 has a translational quantum number of 1. Pi 2 has a translational quantum number of 2. And this pi 3, this is the LUMO of 1,3-butadiene, has a translational quantum number of 3. And from HOMO to LUMO, we have an electronic transition from n equals 2 to n equals 3. So we can compute the energy difference between HOMO and LUMO easily using the particle in the box model. It's 3 squared minus 2 squared times this common factor h squared over 8ma squared. Again, this is the HOMO-LUMO energy gap, and this is equal to the energy of the absorbed photon, which is equal to hc over lambda. We reorganize this equation. Lambda equals 8ma squared times c, the speed of light, divided by 5h. And then we plug in the mass of electron here. We plug in the length of the carbon chain, assuming there are 3 carbon-carbon bonds, each with a bond distance of 1.4 angstroms. And over here, that's the speed of light, and this is the Planck constant. The result is lambda equals 120 nanometers. The experimental value is 270 nanometers. This is because our particle in the box model is a very crude model to describe this 1,3-butadiene. A second reason is I assumed that this 4 pi electrons is fully confined within these 3 carbon-carbon bonds. So if the electrons can be more diffused, we will actually get a larger lambda here, and then that's closer to 217.